I am Abhijeet Chaudhuri. I am currently working as a site reliability engineer at Quartic.ai, and before that I was working as a DevOps engineer at RoboMQ, and he's my colleague Sanskar.
Yeah, hi everyone. I am Sanskar Agrawalla, and I currently work as a site reliability engineer at Quartic.ai, and earlier I worked as a DevOps engineer at RoboMQ.
Yeah. So most of us use Kubernetes every day, right? From deploying pods, managing workflows and services. When we think of Kubernetes, everything seems to be working very smoothly, right? But underneath the Kubernetes lies a series of the gRPC calls that the Kubernetes components use internally to communicate with each other. Every time we run a kubectl command, it triggers a cascade of the gRPC calls internally to communicate between the components inside the Kubernetes to communicate with each other. And when anything goes wrong inside that cluster, it becomes difficult to trace that thing because Kubernetes gives us a very few clue of why and where actually the thing is breaking. From a developer's point of view, it acts as a black box and the developer has no clue what is going inside the Kubernetes. Although this makes it highly scalable and modular, but it acts as a black box from the developer's point of view. So let's understand where gRPC is actually fitting into the Kubernetes. So let's understand this slide with the help of a basic example, right? So suppose we want to deploy a pod. So when we apply the YAML to the cluster, the API server receives the request and the scheduler decides which node the pod is going to be scheduled. Once the scheduler asks the kubelet to assign the node to a particular pod, once the node is assigned, the kubelet then communicates with the container D using a series of gRPC calls. The kubelet invokes various methods like pulling the container image, start container, create container, fetch the container status. All these communications between the kubelet and the container D or the CRI is happening via the gRPC protocols. Similarly, once the pod is successfully deployed, then the API server needs to update the etcd database with the current status of the cluster, again using the gRPC protocols. So each of these interactions form a chain of gRPC rules that underpins the cluster orchestration, enabling the Kubernetes to function as a cohesive and distributed system. So you might ask, what's the problem? The problem, as I mentioned previously as well, is the limited visibility into the gRPC cluster, right? So let's modify the previous example a little bit. Now we want to deploy the pod, but with a volume mounted to it. So in case the volume mount fails, you might describe the pod and see a very generic error message that RPC error, mount volume failed. But it gives us no clue whether it was an NFS backend issue or the CSI driver issue or the node's kubelet configuration. You then end up playing detective, checking the CSI controller logs, inspecting node permissions, and sometimes even digging into the driver source code just to trace this simple issue, right? This process now has turned into hours of debugging. In short, when the gRPC call breaks, it gives us no clue why it is actually breaking, turning otherwise a simple issue into a time-consuming investigation. You might then ask, okay, if the pod logs are not sufficient, we might check the kubelet logs or the API server logs or the etcd logs. You are correct to a certain extent, but these logs are also not sufficient. There are multiple reasons for the same. The first is these logs are static and isolated, right? The API server has its own set of logs, kubelet has its own, and similarly other components has their own set of logs. But they are not connected to each other. There's no view of call of flow. It does not show us how the flow is actually traversing between the different components of the Kubernetes. Another factor is the missing performance insights. Log never show us things like latency or the status code or any other information that can act as a key factor in fixing these solutions. So because of all these things, the root cause always remains hidden. So to truly understand the gRPC behavior inside the Kubernetes, we need the tracing at the runtime layers, and logs are not sufficient for this. So how we can gain the visibility into these internal gRPC calls? So we have explored a couple of approaches for this, and we found that these two approaches that we have shared in the slides suits our use case. So the first solution is using the custom gRPC visibility exporter. So in this approach, we are using OpenTelemetry SDK along with Tempo and Grafana to capture these internal gRPC calls and show them in a visualization dashboard named Grafana. And in the second approach, we are using the Kubernetes built-in native gRPC telemetry instead of using an external agent to intercept these gRPC calls. We'll be enabling certain flags inside the Kubernetes while setting up the cluster, and then these calls will be intercepted directly by the Kubernetes. So the end goal is going to be same. That is, we need to achieve end-to-end observability for across the Kubernetes gRPC layers internally. So let's start diving deep into each of these approaches. So the approach one, which is using OpenTelemetry SDK to intercept these gRPC calls. So if we see the flow chart, right, as mentioned previously as well, that the Kubernetes components use gRPC protocols to communicate with each other, right? So we'll be applying the OpenTelemetry SDK as an hook between these components. What it will do, it will intercept each of these gRPC calls and fetch us the metadata like latency, status code, and other payload characteristics. These characteristics are then forwarded to the OpenTelemetry exporter. OpenTelemetry exporter will then convert these metadata into meaningful spans and store it in a data storage. In our use case, we are using Tempo because we'll be visualizing the traces in Grafana, right? So the exporter will store all the meaningful traces into Tempo, and then Grafana will be reading those traces from the Tempo and visualize it in a meaningful dashboard. But there's one issue with this approach, right? So what's the issue is that Kubernetes itself has identified this problem that we need tracing at the runtime layer. So from Kubernetes version 1.22 itself, it itself has started giving us native OpenTelemetry exporters. So in the approach 2, what we'll be doing is, we'll be enabling those exporters internally. So since we have a shortage of time, we won't be diving deep into the approach 1. We'll be giving a demo of our approach 2, that is leveraging the built-in gRPC telemetry exporters. So in this slide, we'll be enabling certain flags and integrated with Jagger to display the traces. Now the question might arise that why Jagger and not Grafana or any other tool? So that will be seen in the further slides. So I'll now hand over to Sanskar. He'll show the exact steps that we followed and how this setup looks end to end.
Yeah. Thank you, Abhijeet, for the detailed overview approach of our approach. Now I will be forwarding this talk for the implementation and the dashboard visualization part. Now coming to our current setup, the implementation overview and the setup. So the main objective, as we discussed earlier, is to gain end-to-end visibility into Kubernetes internal gRPC communication, which are between the different components of Kubernetes, like between API server to kubelet, kubelet to etcd, and vice versa. Now, as you all know, there are different type of Kubernetes clusters in our market. Some are created by KOPS, some are created by kubeadm. There is AWS provider Kubernetes also, like for Amazon it's EKS, for Azure it's AKS. So it's obvious that there are different approach to configure this thing. But in our approach, we are using a kind cluster. Why? Because it's a lightweight, easy to reproducible for rapid experimentation. So it's good and ideal for the demonstration part. If you little know about wanted to deep dive into kind cluster, so basically the entire Kubernetes control plane runs inside a Docker container, which gives us the full access to component manifest file. So you can directly change those components file as per your use case. And how you can do that? By going inside the Docker container using the docker exec command. Now coming to setup highlight, we have chosen Kubernetes version 1.30 for the demonstration. And as earlier discussed, for the tracing, we are using native OpenTelemetry gRPC exporter. And for collecting these spans, we are using the collector backend, which is OTel collector backend run as a pod in the Kubernetes cluster, and Jagger UI for the visualization part. Now, coming to how we have set up the tracing using the internal KTS exporter. So Kubernetes offer a native tracing configuration API. With the help of this, it can enable the traces for different components of Kubernetes. So there are various approaches to configure this thing. Like we are using custom resource definition approach. So basically, Kubernetes provide a feature flag like feature gate, which will allow the different Kubernetes component to enable the tracing. For that, like for example, for API server tracing, you need to pass the API server tracing true over the feature gate, and it will be enable the tracing for the component API server tracing. Now, once the tracing will be enabled, you need to collect it somewhere, right? So for that, we are using OTel service collector, which is run as a daemon set in our Kubernetes cluster, which is listened on the port 4317. So in the endpoint, we have mentioned the same collector name and the port 4317. Now, this configuration is stored in a config file, which you need to pass as an extra argument over the cluster configuration of API server. Now, with this configuration, the tracing will be enabled for the component kube API server. Now, we will, in the later slides, we will be enabling for the different components, like for the kubelet. The configuration will be same as of kube API server. You just need to pass kubelet tracing true in place of kube API server, and with this, the kubelet config, the kubelet component will start exporting its traces. The endpoint will be same, the OTel daemon set service collector, and same this configuration will be passed as an extra argument over the cluster configuration. Now, till now we have enabled the tracing, and we are collecting this over a OTel collector. Now we will be deep dive into what is OTel collector and how the data flow among them. Now, basically, the OTel collector it acts as a central bridge between the Kubernetes internal gRPC protocol and the Jaeger backend. Now, coming to its configuration, we deployed it as a daemon set, as I have talked earlier. So it will run as a standalone pod on each node to fetch or to collect all the spans of that particular node. Now, once it will receive the span from the exporter, it will handles the batching and sampling and export it to the Jaeger exporter, export it to the Jaeger collector via the Jaeger exporter. Now, there is one question you might ask then, what is the use of this OTel collector? Why can't we directly send the traces span to the Jaeger backend? Why? Basically, the OTel collector is just getting the traces and sending forward to the Jaeger. So then why we need this OTel collector? So basically, when the exporter try to pushes the data, it pushes in the raw OpenTelemetry data, in which it will try to push the raw data in the Jaeger, but the Jaeger doesn't actually natively understand this OpenTelemetry data. It expects in the Jaeger format. So to resolve this, the OTel collector came into picture. It convert this data in the format of Jaeger via its inbuilt exporters. Like in this case, we are using the Jaeger exporter. Now, it also gives us the flexibility, which means if you are not able to stick to a particular backend, like you can also use Grafana Tempo and Datadog. With the help of its exporter, you can directly change in the data form as per your backend. Now, the Jaeger integration in the OpenTelemetry setup. We have using Jaeger for our visualization layer for the internal gRPC traces. The OpenTelemetry collector, when OpenTelemetry collector directly send the data to the Jaeger, then the Jaeger UI display them in a clean, developer and friendly interface. Now, how Jaeger fits into our demonstration? So basically, Jaeger provides us some basic features like traces, timelines, service graphs, dependencies views, detailed gRPC call insights. So there is one screenshot also attached over there for your reference. Like there is one service in the left side of the section. And the kubelet is currently selected over there. So there a drop down will be there. You can select the specific Kubernetes service. Like you can select the kube API server or HCD, and the later there is one operation thing. We have currently selected as sync pod. There are different operations as well. As per your need, you can choose that, and you can choose the maximum time duration or the time range you wanted to see for the particular logs. And with applying this filter, you can get your traces as of your requirement. Now there is one key point to be noted, like we are storing currently using Jaeger, and the Jaeger by default stores the traces in the form of memory. So it's basic, like when the pod start, the traces are lost, like which is fine for our testing and demo purposes. But for your production grade, you should use a persistent backend, such as like in the most common in the market is currently Elasticsearch. You can store the data over the Elasticsearch, or if your use case is like buffering large trace volume, you can use the Kafka. Or if you directly want to integrate this thing over the Grafana dashboard, then you can directly use the Grafana Tempo. Now, with this setup, I think we have currently gained the visibility inside end-to-end of internal gRPC protocol. Now I am inviting Abhijeet for the final conclusion.
Okay, so once this setup is complete, now we can finally trace what is actually happening inside the Kubernetes clusters. So we have added a few screenshots for your reference. So in the first screenshot, if you can see, it is showing us the traces of the communication between the API server and the etcd, right? So it is showing us details like the latency and the status code and other information that can be useful for us to diagnose certain issues. And in the second screenshot, we can see that the traces are shown for the communication between the kubelet and the container D, right? So it is showing all the operations and the methods that are being invoked, from fetching the image status to pulling the image, creating the container, and then starting the container. So now, in the first example that we discussed of deploying a pod with a mount volume, right? So if anything goes wrong in this layer, then it will be clearly visible in this trace, and the developer don't have to debug hours, put hours into debugging this simple issue, and it can be clearly visible into this trace. So what actually began as an invisible layer in the Kubernetes has now turned into a transparent and traceable system. And by capturing these gRPC traces between the components like kubelet, containerd, and API server, we have now turned this guesswork into an understanding. And now, instead of chasing these vague log messages, we can pinpoint exactly where and what exactly is going wrong. And that brings us to the end of this presentation. Thank you, everyone. We are happy to take any questions that you may have now.